Okay, there's still people arriving, but perhaps we already can start. I welcome you to the fourth EACM. So this time it's in Braunschweig. So it's on entanglement-assisted communication networks and related topics. You saw that I hope the booklet is already on the webpage. So we have a booklet where you can also see all abstracts and such things. If you want to join online, there's also an online link. If you have some other days, that's also possible. For the online participants, you can ask questions in the chat. So we will answer them. So we are following your questions in the chat. Perhaps we can also ask you then to tell them in person, but don't speak during the presentation perhaps. So it's really important that that during the registration you sign 2 documents that we get some reimbursed, of course. And that what is also very important for those who will go to the PTB tomorrow and don't have a Deutschland ticket, please put your name there, because we buy tickets for all these people who don't have a Deutschland ticket. So just sign there. So Olaf is at the registration. Ask him if you have some problems, then you will see. Today we have first our main presentation and then talks, and then we have poster presentations and demos at the other side. There also will be the coffee breaks, and tonight is a barbecue. So we will do in the afternoon, we will do demonstrations and posters. They first give a 90-second presentation here, a spotlight, and say why you should come to their presentation and their demo. Perhaps you should go to everyone, I would recommend. And during the poster session at the end, there will be the photo also. And at the end, we start already with the barbecue. That means we have one part where you can sit and eat, and the other part you still can discuss. But if you want to still continue discussing, but the people who present their poster will be there at the poster session, and for the barbecue you can do go if you want. So that's something I recommend. If you have any questions, please be free to ask Bulat, Yanis, Ricardo, or me, or one of the PhD students, or Olaf is also sitting at the registration. And yeah, otherwise, please enjoy the conference. So the first talk we have today is given by Fai Ding. Fai Ding began his academic career at the Institute of Semiconductors, Chinese Academy of Science, with a joint PhD at the Max Planck Institute for Solid State Research in Germany. And he also spent some time at the TU Delft in the Netherlands. And after completing his PhD, he works as a postdoctoral researcher in the IFW in Dresden, followed by a Marie Curie Fellowship at IBM in Zurich. Since 2012, he had led a research group at the IFW in Dresden, and then he got a full professorship in Hannover in 2016, and he received already his first EAC starting grant in 2016, and was awarded as an EAC consolidator grant in 2021 for his continued excellent research. And we are very happy to have you here, and we are looking forward to see your presentation.
Okay. So thanks very much. Thank Christian and also the organizer here for having me here. So it was a great pleasure to see that so many things going on quantum internet, or let's say quantum network, and also in Braunschweig. So first of all, I would like to thank Christian for pronouncing my name correctly, because for many German, they pronounce my name as Phi, you know? So because it's following the German pronunciation, it should be Phi, right? Somehow it's connected to the pronunciation of the face, right? Phi, yeah? So meaning that I have to do something about quantum information. So the talk today is a so-called Niedersachsen Quantum Link. It just started. Today I will just show you some very preliminary work, and the plan is that I can have deep discussion with you guys. Yeah? Okay, so first of all, I would like to thank some people. Yeah, so as Christian already mentioned, I studied in Max Planck in Stuttgart, actually also in IFW Dresden, together with Oliver Schmidt and also Amanda Rusley. So they gave me a lot of help. They guided me to the road of quantum thing, okay? And also I would like to thank my wonderful colleagues in the BMBF consortia. So actually it's a long journey. It's from Quad Rep. So it started from 2010. I think Christian was also there by that time. I was a still student by that time. And then we have QCOM, QLinkX, QRX, and that is more than 12 years of journey, right? So I see, or let's say we together, we see how the consortium grow, and many young scientists, they grow, and we generate a lot of exciting results. I'm very proud of this consortium. Also, of course, I would like to acknowledge my group members in Hannover. So when I arrived in Hannover in 2016, we basically started from scratch. There's nothing. But today we are able to generate some work, and we have a very good infrastructure. I would say I should thank them for the contribution. Okay, so before I start, I would like to motivate my talk with a beautiful movie. It is actually a real movie. It's a beautiful summer night in Thailand, okay? So you see that these are fireflies. So they synchronize their flesh, okay? So it's a really synchronized behavior, or some people, they call it a networking of fireflies. So the thing that, how do they work? So lucky enough, there was a very straightforward, let's say, simulation video. So you see the individual fireflies, yeah? So actually, the fireflies, just like our human being, we have internal clock. Everybody has a clock. You wake up 6 or 7 in the morning, right? Because your clock, ding, ding, you wake up. So the same to the firefly. So when the clock struck 12, they emit a light. So if there's no connection between the firefly, then they will just emit light individually. That's just like our individual quantum device, right? But the thing become interesting. If the fireflies, two fireflies, they're close to each other, they can communicate. Maybe we can do this game. So we say the neighbors, they will be, let's say one firefly will nudge the clock of their neighbor. In that case, you will see that gradually they become flashed together. Now we have a larger scale network. I'm not talking about several tens of fireflies. In reality, there are several 100,000 fireflies that can do this synchronization. That is amazing. That is something we cannot easily do. Yeah. Of course, today with internet, we try to do similar thing. Of course. Yeah. Yes. So now I think I gave you a good example. So from firefly to quantum network. So in order to build a large-scale quantum network, we first have to have small scale interaction, yeah, and then we can have a large scale work. So what if we are not talking about fireflies? Let's say we replace all the fireflies by quantum devices, and the connection between them are photon. Now we have a quantum photonic network, right? So from this example, you see that there are actually two things. First of all, the nodes have to be able to communicate with each other, okay? The second thing that the nodes, all the individual devices, they should be able to be clocked, okay? They should have a clock, and they should be synchronized, okay? Those are two important things here. In the long run, we can dream about a quantum network, of course, but some people may ask, why do you need a quantum network? Or, yeah, so it's a big challenge to do it, right? So there are some potential application, I would say. First of all, is the so-called quantum internet. So you know that there's a worldwide hype on building quantum computers, yeah? So in Niedersachsen, we have the so-called Niedersachsen Quantum Valley, where people try to build up like a 50 qubit trapped ion quantum computer, right? The thing that how do you connect this quantum computer in the future? Yeah, this is one question. Yeah, of course, quantum computer need to be connected by quantum communication. The second interesting thing, which would be potentially interesting also for PDB and the colleague in Braunschweig here, is how do we synchronize clock by using entanglement, or in another word, entanglement assisted clock synchronization. Yeah. So today this is more still on the theoretical proposal level, but there are several groups working on it experimentally. The third thing is very interesting. It's a so-called very long baseline interferometry. Okay. So if you still remember, like several years ago, we had our human being. We had the first the photograph of the black hole, right? So it was very difficult to obtain it. So it relied on the, let's say, the inputs from different astronomical stations worldwide. The question is, how do you synchronize them? So there are people, of course, there are also theoretical proposals say that we can use entanglement to help this process, let's say quantum communication, entanglement-based quantum communication. Of course, there are many other fundamental physical questions. They can be only addressed, I say only addressed by large scale, let's say, entanglement. You cannot just do it in the lab. Yeah, you have to go out of the lab and build the entanglement, long distance entanglement. That is my motivation to do the work. Okay. So experimentally, I would say this is not a science fiction anymore. People are trying to build a quantum network, a prototype quantum network already. Here I show three work just a few months ago, published in May. Okay, the first one is a creation of 3-node entanglement in the metropolitan quantum network in China by Jianwei Pan's group. The other one is from Luking's group. So they build also a network, a telecom network, 3 nodes in Boston area. So by using silicon vacancy center. And also, Ronald Hansen group in Delft, they're doing similar thing by using MV center. Okay, so these are 3, I would say, in my opinion, state-of-the-art work, very beautiful work. So we see 3 systems here: atom, silicon vacancy, and nitrogen vacancy. Yeah, I believe that you will hear more about nitrogen vacancy later, or silicon vacancy. Yeah, so there will be 2 parts of my talk. First, I will talk about a small scale link. So basically, how do you connect 2 firefly or 2 devices by photon? Okay, how to entangle them. The second part of my talk would be how do you build a larger scale. You can take the second part more like science fiction. Okay, this is more like outlook. Good. Now I start my first work. So let's say, how do you connect the 2 devices? Yeah. So this was supported by my ERC grant some time ago. So we call it elementary quantum dot networks enabled by on-chip nano optical mechanical system. It's a long name because we have to catch the eye of the referee. Okay. So what do we do here? We want to develop semiconductor single and entangled photon pair sources with deterministic and clocked, let's say, emission. So meaning that we use quantum dots, semiconductor quantum dots to generate. So as I told you, we need a clock. The emission must be clocked, right? So before I talk about our quantum dots, I would like to start from atom because everybody here are familiar with atom. So how do we generate, let's say, first, there are 2 tasks. The first task is we have to entangle a matter qubit, which means the spin, with a photon, which is a flying qubit, okay? So this is pretty easy. You have a ground state, you have an excited state, and the spin is basically stationary qubit, and then when it decays, it will emit a photon, which is a flying qubit. So basically you can create certain spin photon entanglement. Yeah, I don't have to go to detail because we will have another beautiful talk afterwards about that. The second task is that how do we generate an entangled photon with an atom? So this was a very classical experiment or milestone measurement. So by Professor Alan Aspect. Okay. So this is the level scheme of a calcium atom with excited state J equals 0, J equals 1, and also ground state J equals 0 here again. So basically, you will have a cascade emission, let's say from this state to here and to here, or alternatively, with different polarization, they can go to here and here. So now you will have entanglement of this photon 1 or photon 2, okay? So you can simply write it down in one of the Bell states. If you are not comfortable with the level scheme, you can simply draw the photon like this. Basically, they can be represented by Poincare field. So when you try to entangle them, they will just look like something like this, yeah. So now I move to our system, the semiconductor quantum dot. We call it artificial atom, okay? So we grow it by using the so-called molecular beam epitaxy. So previously in Stuttgart and also in Dresden, but also now also in Hannover, we have our own MB machine. So we grow quantum dots like this. So you see a tiny little structure with a size of several tens of nanometer, yeah. So you can confine the electron easily. The interesting thing that these are semiconductor systems, meaning that we can use all industrial techniques to process them, optical lithography, e-beam lithography, as you wish. So there are some potential advantage of this system. First of all, it is artificial atom, meaning that it can have deterministic and clocked information. When you give a laser pulse to the quantum dot, it will give you one photon, one and only one, not more, okay? The spin photon, the single photon and the entangled photon emission are both possible in this system, just like atom. But something more beautiful than in some sense, more beautiful than the atom system, it has potentially very high repetition rate. So the exciton confined in the quantum dot, for example, in our quantum dot, they can have a lifetime about a few tenths of picosecond, meaning that potentially you can go up to 10 gigahertz regime. People have experimentally demonstrated at least 2 gigahertz repetition rate now, okay? Another thing that I mentioned is compatibility with the semiconductor fabrication technique. Also, this system provides both spin and photon qubit. This is interesting because potentially you can generate repeater with this system. I use the word very carefully. I say potentially because the spin current time is still quite limited in this system. People are trying to improve the growth quality of this sample. But of course, there's some also intrinsic limits like the indium spin, but we don't talk about it here. Another thing which I like very much, this system, because you can do electrical injection. Yeah, so I think a lot of you are familiar with the so-called spontaneous parametric downward conversion. You shine lasers through a BBO crystal, you generate an entangled photon pair, right? So there's no possibility to do electric injection there. But here we can do it simply by fabricating a so-called PIN junction. Yeah, I will show you later. Also, you can do on-chip integration, meaning that you can potentially have a portable device. Yeah. So there was a remarkable progress in the last few years. I would say I have stayed in this community for really many years. I would say over 20 years by now. I see there's a very crazy period where a lot of people, they just drop out the business because it was so difficult to improve the single photon quality, and also it was very difficult to get entangled photon emission from this system. Therefore, a lot of groups, they just drop out, okay, especially in the States. Yeah, but in the last few years, we see a progress really like this. It's not exponential, but it's really going up like this. Yeah, the quality improved a lot. So if you are interested in the progress, I would refer you to the very nice review paper by Pascal Selenat. So she reviewed the progress on the single photon emission from the quantum dot. And I would like to also point out a milestone measurement by Professor Richard Verhoeven group in Basel. What they do, they use the gallium arsenide quantum dot, very much like what I use in our research. So there are two quantum dots that he tried to, he did interfere the two photon, the photon emitted by the two quantum dots, and they can obtain, this is so-called Hannover measurements. They can obtain the indistinguishability about, let's say, over 90% for this solid state system. This is remarkable. Why? Because let's say, I started quantum dots from like 2004 something. So by that time, my supervisor told me that semiconductor is good, but it's dirty. It's very, very dirty. So even one alien atom out of 1 million host atom will destroy your system, will change your property significantly. So people by that time, they believe that the single photon emission will not be very good, not to even mention the interference of the two photons. But today, we have over 90% indistinguishability of photon. This is the really matching the performance of already atom and ion. Okay, I would say this is very remarkable. So this great achievement has enabled a roadmap here. Okay, how can we build up a quantum network? It is not as simple as a Lego. First, you have a spin photon entanglement, for example, in Hannover. Now we have another one in Braunschweig. So now both of us, we agree that we send the photon to, for example, Peine, a city, small city in between the two big cities. And in Peine, we do the so-called Bell state measurement. Then we can harass the two remote spin, okay? This remote spin, for example, can be trapped ion, for example. Yeah, but okay, this is a more science fiction now, it's difficult. You can do also entangled photon, yeah? So now the photon, they are basically, they are information carriers, messengers, okay? So we have two pairs of entangled photon, and we do the Bell state measurement again, we can harass the entanglement over long distance, okay? These two are so-called entanglement swapping process. To enable a long distance communication, you also need memory and synchronization. So the idea is pretty simple. You just store the photon into some system. It can be a natural atom, or it can be diamond, for example, or it can be rare earth doped stuff. So there are many possibilities. So this is like a quantum memory, okay? So when you have these three things together, you have already one elementary network, okay? So this is our roadmap, very easy. Now I show you some selected results from our group in the past few years. As I mentioned, or as I emphasized already at the beginning, it is not my own work. It was a collaboration work with many other people already back to my time, even in Stuttgart, yeah. So here is one device. So this is a chip carrier. We have in the center a tiny little piece of material. This is not semiconductor. This is called, this is a piezo, yeah? This is the PMMPT piezo. And on top of that, which you cannot see by, is a tiny little piece of semiconductor membrane, let's say a tiny thin film containing quantum dots, okay? Of course, we have to do wire bonding. So the semiconductor quantum dot is embedded in the p-doped layer, n-doped layer, and also intrinsic layer is quantum dot, okay? When we give a few volts, which means that you can operate by just battery, yeah? You give few volts voltage to the quantum dot, it will emit single photon and entangled photon. Of course, I still have to mention that why do we need a piezo here? Because the quantum dot is intrinsically not able to emit entangled photon. Okay, so in the past year, people try to look for the so-called the hero quantum dot. They look for thousands of quantum dots. Finally, they find one which is able to emit entangled photon. That's not good. So we know now today we know that you always need some tuning knob. It can be strain as we use here, or it can be electric field, okay, or many other possibilities. This is a good example to show the potential of this system. I think it's a good example, in fact. And also we do a lot of MB growth, okay? So this is, for example, showing the spectrum from one single quantum dot. So this is the quantum dot look like this. So it is the, let's say in the aluminum gallium arsenide substrate, we use the so-called droplet epitaxy to remove some of the material and make a hole. And then we fill gallium arsenide inside, and finally we kept another layer of high band gap material. So this is our quantum dot, okay? So we can use a laser to interrogate or to investigate the system. This is spectrum. So first of all, we try to adjust the amount of the filling material in order to shift the emission to 780 nanometer. Why? Because 780 nanometer is the absorption, let's say absorption of the rubidium. Yeah, so the idea is that we can put one of the photon into the rubidium, so the rubidium will act like memory, and then after some time we can take the photon or take the information out. Yeah, not the same photon, of course. So this emission line, they have almost identical intensity. Yeah, so they're pretty bright. You see that the integration time is 0.01 second, and we can still have like around 30,000 counts per, in this short period. So these two emissions, they're entangled in their polarization, okay? So if you measure the polarization of this one as horizontal, you should have also horizontal here, or, you can do it the other way, yeah? So basically meaning that we are able to demonstrate this one, okay? So entangled photon pair. As I mentioned before, we can change the wavelength to 780, but also we can also grow another, let's say another sample which where the wavelength located at 795 nanometer, because this is a rubidium so-called D1 transition, and 780 is a so-called D2 transition. Yeah, so similarly, you can adjust the filling amount in order to generate photon emitting at, for example, now we can do 730 nanometer, which could be interesting for silicon vacancy people. And we can also grow the same sample, similar sample, at 670, which would be interesting for the nitrogen vacancy people, okay? So we are working towards the hybridization of different physical systems. So meaning that we kind of realize this system, myself, I don't do the memory stuff. We did collaborate with the Dieter Mischer from Bonn, yeah, and also some other group on this one. This is another very nice result, which I liked very much. So we try to improve the brightness of the sources. So as I showed you in the beginning, the fireflies, the flashlight, right? They have to be bright enough, otherwise you don't see them. So the same, the quantum devices, they should be bright enough in your photonic network, otherwise you can neglect them, yeah? These are, let's say, this graph showing the entanglement fidelity of the sources as a function of the brightness of the sources. One meaning that you give one excitation pulse to the system, you will be able to generate one pair of entangled photons, not more, okay, not less. So in the previous period of time, let's say in the past years, so the quantum dots, they can achieve very high brightness. That's a pretty good one, actually. They can get very high entanglement fidelity, but the brightness is pretty bad. You see, this is a log scale, so several order of magnitude lower than the so-called SPDC. Yeah, but SPDC has some certain problem. So these are two results, one from Jeremy Pan group, another one from Switzerland, yeah, a group from Switzerland. So basically, if you increase the brightness, that means you have to increase the pumping density of your laser, then the fidelity, entanglement fidelity will drop quickly. So there seems to be a kind of red wall somewhere. So we try to fabricate some devices. So this is our previous result, but I mean, this is already 2018. Today we can do better. So you see that by that time, the entanglement fidelity was about 90%. The extraction efficiency is also pretty good. Today, I would say we're roughly somewhere here. So the entanglement fidelity can be routinely larger than 95%. The extraction efficiency today is, let's say, from the device should be typically more than 60% is possible. This is a very old design. So this is actually a solid immersion lens where a small, tiny little quantum dot sample are attached. Okay. Today we're trying to adapt some other designs. So this is the so-called circular ring grating design, which are very popular in our community in recent years. We try to do some modification because, as I mentioned, we want to integrate PIN content, right? Meaning that you have to let the current flow, electric current, flow through the sample. That's why in the normal design, if you have really ring, you cannot have electric current. Now we just make this look like a photonic crystal, right? So electric current can actually go through the gaps and then finally flows through the quantum dot. Yeah, we're fabricating this device right now. This is just a simulation. Now I talk about a very important ingredient in our work, let's say, which is so-called wavelength tuning, which is boring, super boring, I tell you, but it is very critical. So I mentioned that building a quantum network is just like building a Lego. But saying that, if you ever played with Lego, you know that there are two types of Lego. There's normal Lego for big people. There's also small Lego for maybe my son, okay? There's a Duplo, yeah? The thing that how to match them is just difficult, yeah? This is the technique I mentioned. So we fabricate a quantum dot inside a tiny film, thin film, and this looks like this. And we put the quantum dot onto a piezo. This piezo is special. It can work at liquid helium temperature, 4 Kelvin. The normal piezo, like PZT, ceramic PZT, they were just frozen. Yeah. So this is shown. Let's say this I showed you before. This is entangled photon pairs, right? Exciton, biexciton. They are entangled in their polarization. Now, as soon as when we manipulate the voltage on the piezo, you will be able to change the wavelength. Yeah, the tuning is very precise. But do you notice a problem? You see the scale here, 1,000 watts. This is something we have to work with in some years ago, because in order to generate some meaningful strain from the piezo, you have to achieve certain amount of electric field. Yeah, and this piezo is pretty thick, a few hundred microns thick. So you have to supply this voltage. So it was a dangerous time. Yeah, we improved that afterwards. I show you later. Okay. Now I showed that. Okay, now we can tune the wavelength, right? But one question is, to which wavelength should we go? Yeah, we should have a agreement. For example, in Dresden, we say I want to tune the quantum dot wavelength to 780. But in Hanover, I say no, I don't like it. I may like 781. Yeah, in Bronx, like your people, maybe I like 790. So we don't have a so-called absolute frequency standard. Yeah. So why don't we just come to some natural standard? For example, we use rubidium. Yeah, rubidium has a certain absorption at 781 or 780.0149, blah blah blah. Yeah, we have to just tune the wavelength precisely to that wavelength. So here we have two quantum dots. They are individually tunable by strain. There's another quantum dot. So now with the beam splitter, we can take a few percent of the quantum dot through the rubidium coil. Here is not memory, it's just a frequency standard, okay? So now we do some PID control. We say, yeah, if the wavelength match, then if the wavelength does not match, we tell the piezo to give a little bit strain, yeah? So after now with this small apparatus, we can tune the two quantum dot emission to exactly the same wavelength, and then we do the two photon interference. So it was a collaboration with JS Michigan. Yeah. As I mentioned before, we have to give 1,000 volts to the piezo, which is ridiculous. Yeah. Sometime I still remember some years ago when I gave the talk, let's say in the Quad Rep conference, one people make a joke. So don't electrify yourself. Yeah. I say, yeah, okay. That's why we try to find solution. The key point is that you don't use a very thick piezo. You use thinner piezo, and you can achieve exactly the same electric field, right? Because electric field is basically voltage divided by the thickness. That's all. Yeah. So that's why we fabricate, let's say, a few hundred nanometers thick, or let's say below 1 micron thick, the piezo. We deposit the piezo onto some platform, which the industry people, they like it, silicon. We deposit it onto silicon, and then we fabricate MEMS structure, so to undercut, and then we deposit electric, let's say there's a contact pad. So in the middle, this is our quantum dot. Now by controlling the voltage on the gold pad, you can change the strain inside the material. This is a cross section. So silicon, this is our piezo, pretty thin. So here, we can just use a few watts to operate it. So it's very comfortable. So basically, you can call it a battery-operated piezo system. Yeah. Another side advantage is that you can, for example, this 100 micron scale bar, you can integrate arrays of devices on top. Okay. Another side advantage, which turned out to be a big advantage, is that you see that we have two pairs of fingers. Yeah, this is one pair, this is another pair. By controlling the voltage, you can decide to which direction you want to give more strain, which means that if the quantum dot wave function is not symmetric, for example, elongated, you can apply the strain to recover the symmetry of your electron wave function and whole wave function. That was actually quite interesting, actually. So my student, Michel Top, so he actually tried to build up some nice idea based on this on-chip tuning platform, and he is working on, let's say, he has started a BMBF junior research group now. This was also a collaboration with IBM, because we ourselves, we don't have the possibility to have very nice integration of piezo and silicon. Actually, I didn't show that between the PMMPT and the silicon, there's actually one extra bonding layer. It's SRO bonding layer. So if you deposit the PMMPT directly on silicon, you will not be successful. This ceramic, this semiconductor, right? They have very large lattice mismatch. Okay, we also, as I mentioned, we grow material, right? So we also try to give our material to different groups. And for example, these are two collaboration results. One is with Czechowicz and also Skonik group in the UK. So they studied our quantum dot. They see how we can polarize all the nuclear spin. Yeah, this is a very interesting result, actually. This is our collaboration with Richard Buffington. So basically, the idea is the same. So we try to interact the quantum dot with the rubidium cell. Yeah, this is actually the scanning of the rubidium cell by using the quantum dot single photon emission. Yeah, by giving strain, you can change the wavelength of the single photon, and then you can scan. Yeah. Good. Now I move to the second part of my talk. So this was supported by ERC's consolidated grant. There are two same or two main goals. in this round. So we want to realize entanglement distribution over large distance. Large distance meaning that from Hannover to Braunschweig, not pretty far away. Okay, 80 kilometers. Yeah, this is the best we can do so far. Maybe in the future we can go to Berlin or go to some other place. But so far, I would be happy with this large distance. And also another crucial thing is, as I mentioned before, clock, time and frequency synchronization. I myself, I'm not clock people, but fortunately in Braunschweig, we have the best clock people worldwide, yeah, PDB. So that's why we work with them. The idea would be like this in the future. Before we go to many, how do you build up how build up the connection between two, right? As I mentioned before, you have to do the Biot measurement, you do the entanglement swapping. This was a milestone measurement by Anton Tellinger group, so performed by Joey Pan as a student in his group. So now here we have two pair of sources, or let's say two pair of sources, three and four, 1 and 2, they're entangled, right? So if we perform the, let's say, Biot measurement on the photon 2 and 3 here, and then we can hierarchize the entanglement between photon 4 and photon 1. We try to do it, or we have done it with semiconductor system. This is our experimental platform. This is the emission, how does it look like? As I told you before, this exciton biexciton depolarization entangled photon, and this was a very nice experiment also by Michel Top. Yeah, so he was also won the Quantum Future PhD thesis award with this work. This is the result. This is so-called two-photon density matrix. So left side is that we don't perform the Biot measurement and measure the photon 1 and 4. Okay, you see this is just a classical correlation. Yeah. But as soon as when we perform the Biot measurement on the intermediate photon, we create this psi minus state. Also, the imaginary part is basically very clean, okay, showing very high entanglement fidelity of about 0.8. So also we show that this experiment actually violates the Biot inequality with the Biot parameter of 2.2. Yeah. So now this measurement, actually we played a trick here. We use one quantum dot, okay? So let's say we do a time multiplexing. So at time window 1, we take one pair of photon, and then for the time window 2, we take another pair of photon, and then we do the swapping. Because by that time, it was difficult to have two quantum dots with identical emission. We are working on that. So for example, now these are two different quantum dots, quantum dot 1, quantum dot 2. This is very entangled, they're entangled, but now we are able to bring the emission of two photons into resonance here. So, but of course, as you can see, the signal to noise ratio of the emission is pretty bad because they are not in the cavity. So we still have to work on that. So this is the idea. So we're still working on this. So entanglement swapping with two remote quantum dots. Yeah. Now let's go out of the lab. This is the end of the talk. Yeah. So every measurement I mentioned is in the lab on the scale of 1 meter is the microcent interferometer, but the thing is very easy. You just go out of the lab, use the dark ground fiber between our two cities. Okay, the physical distance is about 79 kilometers. And then this is a brief introduction of this fiber. It's not fiber built by myself. Okay, it is a rented fiber. So we rent together more or less with PDB, with Stefan Cook group. So the fiber is pretty old. So actually, it's 28 decibel loss inside. So if we use today's standard fiber, the distance is equivalent to 144 kilometers. Pretty good value, I would say. And this fiber is part of the so-called ClockNet DS. So this is the European clock network. So we have many clocks in whole Europe. Yeah, meaning that in the future, if we really can go to larger scale, this would be the way to go. This is a real large scale. There are some technical parameters. We don't talk about it. So the fiber was previously used for time and frequency, or let's say clock dissemination, but now we put single photon, and I hope very soon we also put entangled photon inside this fiber. Another key element here is the telecom single photon sources. This is the circular ring rating sample from Peter Michel's group in Stuttgart. So we have quantum dots inside, and then because the per cell enhancement, we can have very bright photons. So at 1550 nanometer, the sources give you roughly 14 million count per second. So with a repetition rate of 200 megahertz. So finally into our detector, it will be around 4 million counts. That's a pretty good value. So if you don't have enough brightness, the photon will not be able to make the trip from Hannover to Braunschweig, right? Talking about 28 dB loss. So this is the so-called single photon purity measurement, or G2 measurement, measured at 200 megahertz and also 1 gigahertz. In both cases, you see that the G2 at 0 time is exactly 0, not exactly, but very close to 0. So meaning that the single photon still have very good purity after this long travel. And this is our measurement. I would say the preliminary measurement, because we do the quantum key distribution measurement. This is not our final goal, but in order to show that this fiber really works for quantum communication, we use QKT for demonstration purposes. Okay. This is the measurement of QKT performance over a period of more than 24 hours. So this is quantum bit error rate. So it's on the order of 1%, and also is super stable. If any one of you work with commercial QKT module, I think you will appreciate this number, because normally they offer you roughly 5% qubit rate. Yeah. Because actually, if you have a qubit rate of below 15%, you should be able to perform QKT already. But now we have only 1%. This is the secure key rate. Yeah, so meaning how many kilobits per second key we can generate. So we can generate, let's say, in different cases, if you calculate with the so-called finite key, or if you calculate in the so-called asymptotic key, so this is more like ideal key. This is more like where it is really useful for really key encryption. Okay, so in both cases, I would say it's very good value, a few thousand kilobits per second. So it's a collaboration with Stefan Kuhn and also Peter Michela, and I would like to thank also Harald Weinforter for the discussion during our whole project. So this is the results from our paper. This is a secure key rate as a function of the transmission loss, or you can understand as a distance here. So these results are these are the result from our fiber spool in the lab, because here you can change the length of the fiber. This star here is our actual measurement over the 79 kilometer fiber, let's say the dark fiber, the field test. Okay. In terms of secure key rate per pulse, we have only one competitor so far. Let's say this is the result, published in last May by Zhengwei Pan's group. So this is based on the decoy state. Yeah. So this is their key rate is about 5 times higher than our result, I would say. But I have to say that our sample are not optimized yet. So if we calculate our system with the best, let's say with the achievable extraction efficiency, meaning brightness, and also detection efficiency, for example, we should be able to surpass the decoy stage. This is the best decoy stage so far. And for references, these are results from the previous time. People use different systems. Yeah, so their secure key rate are basically several order of magnitude lower. So this was the work done by Jing Zhong, and also he actually also won the Quantum Future Award in this year. Finally, I give you one interesting comparison. So we take one commercial QKT system, And we compare it with our QKD performance from our quantum dots. Yeah. So of course there are slight differences in the measurement. One is measured with a dB loss of 25, another one has 23 dB. But okay, we have higher loss in this case. We measure at a higher loss. We can see that the secure key rate of the commercial system, let's say, is about 167 bits per second. In our case, we have over 10,000 bits per second. And in terms of Cuber, so this is a commercial system, this is standard, about 5–6%. Yeah, so this is very standard, I would say. And in our case, we have below 1%. And also you see the fluctuation is very, very low. Yeah, but okay, this is just for comparison. This is just only to show our sources because it is a deterministic source, so single photon source, so it can achieve such good value. Okay, let me summarize my talk. I hope that I have convinced you the semiconductor quantum dots, they are deterministic and clocked single and entangled photon sources, meaning that they have great potential in building a large-scale quantum network. But of course, we have people working on different material systems here. I have to make a disclaimer. I myself, also, I don't think quantum dot is the best for everything. It is the best sources, but in terms of memory, it's still lagging behind. And also, we can have direct creation of entanglement in the telecom. The small-scale quantum network, let's say with 2 or 3 quantum dots, is on the horizon. I'm very optimistic about that. Then we can achieve similar results to the people who have done with silicon vacancy or the other system. Yeah. Our community is working very hard on that. One last point, the larger scale quantum net will rely very stringent time and frequency synchronization. So this will be combined with the quantum metrology study in Braunschweig. So also, I would like to make a short advertisement. So just a few months ago, the journal Light Science and Application, it is a Nature journal, they have established their first Germany office, and it is in Hannover. So I'm responsible for this handling of the manuscript from the German submission. So if you're interested to submit to this journal, please talk to me. You're more than welcome to talk with me. Yeah. Okay, so finally, thank you very much.
Okay, thank you for this very interesting talk. Are there questions or comments? Yeah.
So, what's the catch? I mean, this seems like a wonderful technology. What are the shortcomings of it?
Where's the shortcoming?
Yes.
As I mentioned, this is a very good source. They can emit photon very efficiently, but their spin coherence is a problem. Their spin, if you wish, you can call it a shortcoming. Yeah. But people are trying to use different methods. Let's say maybe by using a technique so-called dynamic coupling, decoupling, so you can decouple the nuclear spin, so you can, let's say, enhance or elongate, make the spin current time longer. Okay. Or you can, there are also other people, for example, in our community, QRX community, they try to fabricate a double quantum dot molecule. Some theoretical study suggests that the spin coherence may be improved in that system. So yes, spin is more or less the shortcoming. If you ask me the same question like 10 years ago, I would tell you a different story. I would tell you that the extraction of photon out of the sample was a problem because it's a high dielectric matrix, so you cannot take the photon out. But today we have many different beautiful, let's say, photonic design. People can achieve more than 85% extraction efficiency and still going up. Yeah. So I would say that's not a problem anymore, I would say.
Yeah, thank you for your talk. Could you go back to the slide where you show the key rate comparison?
This one?
Yeah, I just want to run.
Yeah.
Thank you.
Okay. This is also this is the internal discussion, unpublished, please. Yeah, because this is involved with the commercial system. I don't want to say the name, otherwise it's dangerous. Yeah, but I would say this QVR of 5% is roughly a commercial standard. I would say, yeah, it's not that confidential.
I have a slightly more technical question.
Yes.
So the emission from the quantum dots can be
Yeah.
quite broadband.
Yeah.
And for rubidium specifically, how much does this impact the performance?
That's a very good question. So that's why more or less the coupling between the quantum dot emission to the rubidium, this business is kind of suspended by now. I can say, because the bandwidth of a single photon emission is roughly on the order of gigahertz. Yeah. So the rubidium, if you talk about single rubidium, let's say a single rubidium atom, so the absorption band is on the order of megahertz. Yeah. So if you go to rubidium vapor, if you do some trick, it can be extended to 100 megahertz at most, but it will be very difficult to go further. So meaning that the rubidium will be just like a bandpass filter. Okay, so we will have only 10% of the single photon at most to be absorbed by the rubidium. This is a big problem. Yeah. So there are possible ways to reduce the line width of the single photon emission from quantum dot. I would say with the best sample today, our quantum dots, let's say the line width can be below gigahertz. It's possible, definitely possible, but still there's a mismatch, unavoidable mismatch. Okay. Yeah. But on the other hand, I have to mention that my personal interest already lie into a telecom emission single photon sources. So in that case, we could have, let's say, memory with broadband. So on the order of gigahertz, possible. Yeah.
I have a technical question regarding your plot, the slide before. Yeah, this one. So you plot here this key rate per pulse. In terms of absolute rates, what can you achieve with quantum dots?
Yeah, that's a very good question, because the security rate per pulse is more a fair value to compare different systems. Because, for example, the decoy state here, they operate their source at 2 gigahertz repetition rate, while we're working with 200 megahertz. So there's already 10 times differences in the repetition rate. In terms of absolute key rate, this is I would say in this case is about 100 megahertz. I would say we are below megahertz, yeah, but close to megahertz per second, yeah. Yeah.
And then one second question. Where do you see the opportunities to kind of like relax constraints in terms of cooling of quantum dots to make it more commercially viable to use them actually?
Yeah. Yeah, we are actually working on that. So for example, for all the QKD modules, we're now trying to build like a 19 rack system. But in the meanwhile, we're working on also putting the sources in a rack. Okay, so how to do that? There are many beautiful demonstrations from the community, not from myself. For example, from Berlin, they put the quantum dot into a stirring cooler. So that will bring the temperature to about 30 Kelvin. So for our gallium arsenide quantum dot, it's still favorable temperature. So we're working on that, trying to see whether it works or not. Another alternative may be, for example, from Munich, from the company like AtoCube, and also from the university, they work together. They try to reduce the size of the liquid closed cycle cooler. So they also make it 19-inch compatible. Yeah, so that's of course another possibility. So I think both are fine. Yeah. There's a way to go, but I don't think cooling will be a problem today.
Okay, perhaps finally, a very general question. You start your talk very nicely with some possible application in the future. What is your opinion? What will be realized first? And do you have a vision of the timeline?
Oh, frankly speaking, I want to collaborate with colleagues from Braunschweig, from PTB, and also from Max Planck I mean, the idea is to explore the fundamental question that can be addressed only by long distance entanglement, right? This is our strength, I would say. The first application, reasonable, I would say, is probably, let's say, using entanglement, long distance entanglement, to study gravitation physics. Why is that? I mean, maybe last year you can still call this science fiction, but there was a recent publication from Vienna, from the Walter group. They showed that they sent the entangled photon through a 10-kilometer fiber spool, and then they see how the rotation of the Earth will influence the entanglement property in this fiber spool. Yeah, so this was a beautiful measurement, I would say. And also, I also know that they had like a 10 million euro ERC syndicate grant to work on this one. So from physics point of view, I see it is straightforward. It should be possible. Yeah.
Okay. Okay. Yeah. Okay. Then thank you a lot for your talk and answering all these questions.
Thank you very much.